of my PhD project, and it's basically about the content privacy in one of the candidate of next generation network. It's called the NIM data network, and we are proposing a method in order to keep the content privacy in an efficient way and a secure way. So this is the outline of my presentation, and we will start by introduction and the motivation of my work, and a quick summary of the NIM data network architecture, and the privacy, and we will talk about the privacy and the privacy issues and their countermeasures, the current countermeasures, and our algorithm, our proposal for this work, and we have a test developments and test results, and we are going to talk about those things. So introduction. Here we are using an IP network. It's based on a point-to-point communication network, but in the end, it's not relying on a point-to-point communication network at all. So it's a completely new design comparing with a point-to-point design. It's basically content-centric network design. So basically, why we need that is an increase of the social media and the caching servers and the YouTube, Netflix, as nowadays we are seeing everywhere. So that's why we just conclude that we need a content-centric networks. So at the moment we are using a content delivery networks, which is IP-based. So basically we have some mirror nodes around of the world. Those mirror nodes are caching servers, and they are replicating the producer of the content. But in the end, it's not relying on IP at all. So basically it's a in-network caching, and everybody is caching the content, and content is everywhere. But this is a proposal in order to overcome the IP limitations. So does it solve the problem? Yes. And does it increases the content distribution efficiency? Yes. But does increase the privacy risk in the network? Yes, because the content is everywhere, and it's cached, and it's ideally secured, but it doesn't mean that the content privacy is totally protected by everywhere. Because at the moment, nobody cares about the privacy. Just the systems are based on how we're going to cache, how we're going to increase the cache. That's it. So there is one methodology to expose the cache informations by the in-network caching servers. So it's called a side channel timing attack. But this timing attack is easy to deploy. It doesn't break any security features of the network or the design. It's simply it is very simple to deploy. It's very easy to use. It doesn't break any security algorithms. It's totally legal, by the way. So the motivation of work. So we have, in order to mitigate this timing attack, we have some countermeasures algorithms in order to mitigate this attack. And they are basically manipulating of the retrieve time by the NDN router. And this manipulation may affect the performance of the attack. So these are the current methods that these are proposed by the other works. But these are affecting the content distribution efficiency very badly as well. So which is in the end is based on increasing the content distribution up, but these methods making it down. So that's why in this work, how we're going to mitigate this issue in an efficient way. So this work try to answer this question: how are we going to protect the cache efficiently, and how are we going to keep the content distribution in an efficient way? This is the quick summary of mean data network architecture. So basically, it is instead of like a end-to-end packets, we have two basic packet types. The interest packet has been created by its user. So basically, it's meant to ask the data packet from the in network. The data packet can be located in anywhere till the interest packet goes anywhere till finding the data packet, till the producer. So it basically based on the human readable names. Everything is human readable in those data packets. So they are also signed by their producer, and each data packet illustrates their public keys in order to keep the integrity of the packet. So those data packets, whenever anybody asks, those data packets are caching by each of the named data network hubs by certain content store policies like list, resume, used, or FIFO, you name it. So there is in this figure, we are illustrating the forwarding and the routing strategy of NDN. This is also quite different than IP network because we have in NDN we are using an application layer. So those popular, in order to find the popular content, deciding those routing strategies, all done by at the application layer. And also in the third figure, it shows how the content are caching by its softwares. So in this figure, we are illustrating a basic timing attack issue in main data network. So whenever a content has been cached by the first facing router, they may have some private information of its producer, of its consumer, of its data packet size, of its signature, like you name it, everything. So to get that content, is it easy? Yes. Is it legal? Yes, because anyone can ask for any content in NDN because of this is the design of the NDN. So what adversary does in here, it uses a timing differences between cached and uncached packages. If it's cached, the timing difference of the data packet, it's lower than the uncached one. So the adversary deciding that these contents has been cached by somebody or by some entities in this network. So then it's focusing and investigating of that content in order to succeed the attack. The RTT can be used for routing strategies as well. And that's why in this work, I just name it as a content retrieve time to illustrate the cache contents in NDN. Also, as I described before, that the attacker does not compromise anything for the security in NDN because anyone can get anything in NDN. NDN is like I make the similarity between NDN and torrent network. In torrent network, whatever you get, you also share with other ones. It's very similar, but in the names, using the names. For countermeasures, the countermeasures also manipulating the response time of the router. So this can be done by the application layer, and the contents can be delivered within a delay, and this delay can be cryptographic, random, fixed delay, and there are like outcomes of each countermeasure methods. By the way, these countermeasures are fixed. I mean, we are using those guys in IP network at the moment, but these are also suitable for NDN as well. And there's an unreadable names approach, which is using an encryption methodology to make the names unreadable. So when the name is unreadable, nobody can guess has been cached. We cannot ask that content by the first facing author. But this approach it doesn't make sense for NDN because those unreadable names cannot be asked by anybody else. So everybody needs to ask the content. Yeah. So but this makes the perfect privacy of NDN. So there is another method we can turn off the caching. So this is totally disabling the content distribution methodology, but this is the best way to mitigate the timing attacks. So beside of this work, if I'd like to give an example, we have like a meltdown attack in our CPUs. It's a physical damaging. So what our updates, our patches does, basically turning off our cache memories inside of our CPUs. So this little bit similar, but it's different one. But it's the same ideology. It's a timing attack and filling the cache, making the processor run more, and physical damage in that case. Also, there's another approach. I call it a consumer-derived approach. So this doesn't make sense to me as well, because this is like if I say YouTube has to be private. If I put a private name in the beginning of YouTube.com, it would be private and it not be cached or unreadable names. But for me, it's private. But for other one, it may not be private. So those consumer-driven approaches are not suitable for countermeasures as well. But the most solution is the random cache, artificial delay, and the turning off the cache. So this is our work algorithm. So it looks like a little bit complicated, but I will try to make it a little bit summarizing the algorithm. So basically, what I say in this work, let's investigate the adversary behavior inside of the network while attacking the router. So is there any like a leak of the attack, or if we are we able to find the adversary face or the attack router? If we able to find identify attack router, and we can switch to those countermeasures that I talked with before. So during that time, we can keep the integrity of the content distribution efficiency and keeping the privacy of the contents in the router. So we have a multi-level countermeasures here. So during my experiments, I mean, usually everybody like to say the same thing in the papers, but in my experience, I decided I make a level of the countermeasures, like a small effect, middle effect, and hard effect. So my algorithm start by a delay case, which is little bit good than the random phase, because when I do on my simulation, I find out that the delay phase is little bit good than the random phase, and the crucial phase is no cache at all. So what does the algorithm does? So basically, whenever I assume that the hop count of the hop count can be used to identify the adversary phase. Who is going to identify the hop count? The application layer. So we have three applications there in NDN. So the first one is the main data network forwarding daemon. So this hop count can be get by NFT. So whenever the hop count is higher than our threshold, I indicate the attack is detected. So while this attack is detected, I apply those countermeasures one by one. So if in the first case, I apply delay, then I wait a little bit and check the values again for those threshold values. If the attack still exists, I switch to the random case. Then, if attack still exists after checking the threshold values, I stay in the null cache. So while the attack is exists. So in order to make the results more realistic, I use a real, this is a simulation work, by the way. I use a real data set from ANT from 2002, I believe. So there are like 625 nodes. So basically what we have done, we have created our adversary model first, which is a unique model. Then we apply to this topology and run 10 times and locate it randomly in for each algorithm. So what our adversary does, I mean, strangely enough, I mean, whenever I make results, analyzing the results, I find out that whenever we ask any content for the router, so it gives the prefix of the content, like a piece of the content. So one content usually divided by 8 segments, minimally 8 segments. So if you ask any content to the router, first facing router, if this one has been cached before, so you get that segment cache at that time. So this is like a very scary for me, because you don't need the whole content for adversary, because you need to define the cache contents in NDN, and an NDN router has to act like that, because if you ask anything, it has to reply with its segment or with whole content. So we have in my previous work, I use a cache hit ratio. So this is also I use to analyze the attack performance in NDN. So whenever adversary uses the timing attack, the CRT timing attack, it uses it increases the router cache hit ratio also increases. So these are the different policies I applied. And I also applied in the last 3 years the countermeasures, like a default countermeasures I make it. So as we see, if we're able to apply the countermeasures directly, we also mitigate the attack efficiently. But this is not a defense and defend attack. This is a fixed. We haven't applied our algorithm to the simulator yet. So this is a basic result. So another, for this paper contribution, we have a hop count. As we see in the figure, the first hop count is much more higher than the no attack, comparing with the no attack model. So this value can be used to find out the adversary faced while getting under attack of the router. So we have a new development for the attack for this work, and we are proposing a hop count and the cache hit ratios in this work. And we are also saying in this work that the performance effect of the countermeasures can be mitigated by defining the adversary node while attacking the node. So possible works and discussions. As I said, this work is not we couldn't able to put our algorithm to our implementation yet because there was some limitations of the code, and because there are lots of limitations on the code. We haven't finished it yet, but the next step can be voice over NDR, the system, because it's a different model, and we can use a certificate, a public key attack on this voice over IP model, and we can configure the NFT for the identifying the adversaries. That's it.
Any questions? Well, me, I don't have a question. It's rather a comment. But at a certain moment, you say that no one cares about privacy.
Mm-hmm.
The thing is that everyone cares about privacy, but no one does a lot to ensure privacy.
Yeah.
And well, that was only a small comment.
Usually we are living in a world like making the contents, sending the contents, receiving the contents as soon as possible. But it shouldn't be like that. I mean, like we should take care of the cache a lot because nowadays the cache limits also increased, and we are like comparing with like 10 years ago. And our colleagues mentioned about the IP network, so there are like lots of cache involved in those works. So the other work is the key.
Second?
The second work also has a
Yeah.
cache somehow.
Yeah.
So I mean, I can get the certificate key, and I can easily define whoever make it the payment in one time by those certificates. So just asking the public key, and public key it's visible to everywhere. And also, I mean, whenever I ask any student, I don't know, I can get your type on it.
Sure.
And whenever I ask a security guy, they say that, okay, everything is secure, like symmetric keys involved, but also the privacy leads also security as well. Okay.
One more question? Thanks.